Okay, so mine is not quite as fancy as the others yet, but it's getting there. So this is Miranda. I showed it last time. I have the full ROS stack working on it almost. So I'm having problems with move base on this thing. If there are any move base experts out there that want to consult with me, I'd appreciate it. This thing does global planning just fine. Can figure out how to get around my house, but when it does local planning, it likes to run into things. And I have yet to figure out why it would do global and not successfully local. The LiDAR shows up on the maps all fine. This thing also has a bunch of little time of flight sensors around here, act as drop sensors. So my goal, if I didn't have so many things going in my life, would be next month to have this thing do essentially all the challenges that it's physically adapted to do with one robot, with one program, in one evening on this thing. So that's where I'm trying to get with this. But I'm trying to do it in the right way. So I'm in no hurry to demo this thing running off the table and surviving phase 4 of the table bond challenge or something like that. I'm trying to get it so that it knows where the table is for the right reasons, and if you throw things in the middle of the table, it recognizes this as a thing to ignore or a thing to pick up, and I should be able to tell it to find the red object and throw it in the blue box and all that sort of thing. And it's getting reasonably close on all of these things. And I don't need move base. Move base is not needed to solve any of the challenges, but I'd kind of like to get it to go. So if anyone has any ideas about why global planning might work and local planning doesn't, appreciate hearing about it.
What are the various things on it?
Okay, so the processor is an up processor. For those of you who run ROS, you may know that some parts of ROS require the Intel instruction set. So on Raspberry Pi, most people don't run those things, but I do. So particularly things involving video processing. So this up board is was like a $160 board, and it's a pretty darn powerful board. It's running 2-point-something gigahertz. I think it's quad processor on this thing, a lot more memory than a Pi. Let's see, there's an IMU, the 6050, just like was it Mark was talking about here on this thing. In the front, there's a Euclid box, which is a robot in a box. But as people who are running RealSense will find out probably in another week, that Intel likes to drop support for all their products about the time that you buy them. So good luck making it to China and still having support with your product. It's a pretty neat device. It's just that Intel never even finished getting it going before they dropped support. It's got a Wi-Fi thing, which if it's in the presence of my Wi-Fi network, connects to it, and if it's out of the range of the Wi-Fi network, acts as a hotspot automatically. USB hub on top of here. Inside there's a RoboClaw motor controller. Underneath here, these little extensions are time of flight sensors. The I can't remember what the chip name is. LX 050, something like that. Pretty neat sensors. And there is a multiple computer setup. So there's a breadboard in the center. I don't know if you can see it in there. And that breadboard has a Teensy 3.6 on it. So the Teensy is running all the little sensors on there. There's also in the motor controllers that I 3D printed down here. You probably can't see, but I've run up temperature sensors into those things as well. And if only I was paying attention to them. When I was driving this thing around in my living room and it was running into things, I'm running it at very low velocity just so I can see what the planning thing is for a long time before the planning vector disappears from the ROS display. So this thing runs into my coffee table, and it's the 500th time that evening that it's running to the coffee table, and I thought, well, I'll just leave it there, and I'll get a hold of it later on, and all of a sudden the motor stops working on this thing, and the wheel won't even turn anymore. And I pull this thing up, and I don't know if you can see, but there's a bulge here where this thing is overheated, the motor fried on it. And I put the temperature sensors in for that very purpose, to detect this. I just haven't turned on the software to actually pay attention to them. Is there anything else? The batteries are these LiPo batteries, and have this high-tech solution to hold the batteries in place here. A little screw into the side. I'm finding that the LiPo battery over here is getting very spongy. If anyone knows how spongy it can get before it bursts into flames, I would like to know that too. Let's see, there's a voltage display on the back on this thing here. You can see lots of pretty lights come on when I turn this thing on. I think that's probably, the LiDAR on top is from Anito.
Yay.
I had a $450 RP LiDAR on there, which I ended up frying. But the RP LiDAR sounded like a banshee on Halloween when it spun around. This thing is dead quiet. The RP LiDAR was a little noisy. This thing is pretty darn stable. I've got a Scans LiDAR at home, if anybody's invested in that product before they went out of business. And the Scans LiDAR is interesting because this thing gives you 360 readings per revolution. The Scans LiDAR gives you a reading whatever it damn well feels like. And they make a big deal out of it. No, we don't give you 360. We'll give you them sometime. We'll give them at whatever rate we damn well feel like. It's okay if you've got move base and AMCL and everything else set up to average the things out and keep the things persistent. But you got to figure it out. So I think that's it.
My name is Matthew. This is my first time I've attended one of the homebrew robotics club. I almost made that mistake because I so confused you guys with the homebrew computer club. I know the history of the club, and I have to say it's really inspiring. I run a maker space over in Cupertino called Cooper Tinker Space, and we're just huge fans of the whole history of homebrew robotics club. And I met a few members at a few computer history museum meetups, and it's a huge honor to be here tonight. And this is just a small project that I've been working on with a few talented animators. I'm interested in social robotics, so I'm really interested in the transformative technologies on how robots can really communicate better with people. So from that, I've been looking at different ways to better use mechanical systems and motion control theory and apply that to different ways that people can find robotics appealing. I discovered a pipeline that you can take animation from. Does anyone know what Maya is? Autodesk Maya? So you can take Autodesk Maya animation and you can pipe it over to an Arduino robot. So for the past few months, we've been working on a few robots that actually use Maya to control as a control mechanism. We have a robot rigged up right here inside of Maya, and if I hit stuff, you can actually see the robot. And this entire system right here was rigged up inside of Autodesk Maya. All of the motions for this robot were completely rigged up in Maya, and then we have it piping over to the actual robot here. It's a small drop in the bucket. I wanted to start with a quadruped because I know that quadrupeds are the complexity of getting motion control movement with in robotics for quadrupeds is really challenging. But I was able to hand it off to an animator. He was able to rig up the system, and each one of these nodes right here, as it's moving across, is linked to a servo. So we can then pipe in a variety of different, using techniques from animation and also techniques from robotics. We're able to develop a lot more advanced robotic control mechanisms that we can use for conveying motion, conveying appeal. I have a few other animations set up on this as well, where the robot is able to move like a cat. We have more complex movements here. Let's see if I can change it out. I don't want to risk it, but because everyone knows, you said you do one thing different with one of your robots, and then the whole system breaks.
No, that's pretty standard. Go. Yeah.
So we have a few animations that are currently set up with the system. And I'm really interested in designing a few other robotics designs. Right now, this comes from an open source build. I want to apply it. Whoa! So you can actually see some of the movement right here. Actually, I think this one's not. So you can actually see that as I keyframe each one of these movements, the robot transponds in real time to the movements of the degrees of which the rig is moving. We're still working out a few of the kinks. We've done a few walk cycles. We've started with the 5-degree robot arm, and we're working on our way to building more complex systems. The next step is I want to make this wireless, so I can actually save wireless, and then on the SD card where I can actually save a lot of animations, and then move it to a more advanced robot. So,
Pretty slick.
What's this robot for you?
How many servos on each leg?
8 servos.
How many?
8 servos.
Total?
Total.
2 on each
Yeah.
leg.
Yeah. We're starting small, but we're working our way up.
Looks great.
Thank you very much.
Thanks for coming.
So Bile's that other bot I showed last time. It's my table bot, and I learned a bunch of stuff doing that thing, and we'll just talk a little bit about that. So here's Bile, and on this thing there's one of them VL53L1X rangefinders, LiDAR rangefinders on top, the red thing there. There's another one from Palolo down at the bottom, kind of there. You can see it on the bottom edge of the thing. And they both have the same I2C address. And I was going to use these things to do TableBot, to scan the table, find the block, find the goal, see the table, all with one sensor. So that's something else I want to kind of just touch on real quick. But anyway, because we're on the same I2C address, I tried really hard to do the thing where you write to it on PowerUp and you change the I2C address. Could not get that working. Spent an entire day beating my head against the wall. Sorry. So I finally got one of these things from Adafruit. It's a I2C Mux, and the thing works really well. It came right up, works like a charm. It's really nice. So if you've got stuff you want to share on I2C, highly recommend this thing. The code is trivial. There's a little routine there with like 4 lines of code, and then you just use this TCA select thing to pick which thing you want to talk to, and you're done. Really great, love it. That's the first thing I kind of wanted to point out. Next thing I wanted to point out is using this LiDAR, the VL53OX. It's a 4-meter LiDAR, so I thought this would be great. It's just a single point, but it turns out the thing is not, it's not like a laser pointer, where you've got like a spot, you can detect the range on it. Apparently, it's, I'll try to tell a little bit about it, but whatever. It has a 27-degree field of view. So it's like a big, broad spotlight. So trying to detect something small on a table like a 2-inch block is kind of not going to work. You don't get enough of a return off of that, and it's just it's lost in the noise. They also have a setting where you can change it to a 7-degree field of view with this not small enough. It just doesn't work out real well. So I captured the scans on the table, and somewhere in here, I just decided to look at the data in Excel just so I could see what the robot's seeing. Who needs ARVIS, right? So somewhere in here is this 2-inch block. I'm trying to go, okay, it's in there somewhere. I don't know, man, where did it go? But if you kind of look, there's a kind of in the middle left, there's a spot where it kind of drops off, the range kind of drops suddenly, where it suddenly gets a little shorter. Well, that's where the block is. So the trick was to then write code to somehow interpret this data and see the block and go find it. Anyway, it was interesting. Turned out to not be that great. I could detect the block once in a while, but a little too small.
What sensor was this?
This was the, it's an ST micro sensor.
It's time of flight sensor.
Yeah, I guess. It's a LiDAR or laser-based rangefinders, the VL53L1X, I think. They have L1X and L0X, 2-meter and 4-meter rangefinders. And they're good for detecting like walls and larger objects, but not for small stuff because the field of view is too big. So,
Ralph, that 7-degree thing, that's news to me. Is that only on the one version, the newer one with the bigger?
Great question. I'm not sure if on the L0 exhibit does that or not, but you have to poke around and look into the API and figure out what registers to write to change the field of view. And basically, it's got a 16 by 16 array. What you do is you tell it, I want to look at a 4 by 4 array, which is the smallest one in the center. You do that. And it still wasn't super great, but anyway, fun stuff about that particular LiDAR. Next, on the bottom, I put new motors on. These are ones that Mike turned me on to for Lyle. These have the metal gears instead of the plastic gears, and they both have encoders, which I didn't have before. So I'm trying to control Lyle so he goes straight, because I want to do floor bot. And if you were here last time, you saw how wonderfully straight he went across the room, right? Not so much, right? So trying to fix that. And I tried just matching encoder counts, but that assumes like your wheels are the same diameter, or your tracks are the same length, or they're aligned correctly, etc., right? There's certain assumptions with just matching encoder counts. So that wasn't working so well, so he was pulling one way or the other and things like that. And also he would kind of wobble around speed-wise, because you've got your sampling rate and speed running at, things like that are also variables. And so, you know, he would kind of oscillate. He wouldn't really maintain a fixed direction, things like that, just matching encoder counts. So I heard they had this thing called a PEZ loop or something like that. No, it's a PID loop. And I started looking into PID loops, and you know, it was like complicated. You know, there's some math there. There's like matrix math or triple integrals or something. I forget what. And just a little daunting. And I'm trying to get him ready in time for the challenge, so I don't have a lot of time. So I got the gist of how they work. You know, you've got these three terms, KP, KI, KD. Those are your three coefficients for each of the three terms, your proportional, integral, and differential correction factors, if you will. And I said, how hard can it be? So I wrote my own PID loop. So this is like PID Lite, I call it, because A, it runs on the Arduino, and you can't do too much there. And I just kind of like took sort of a high-level view of what a PID loop is and wrote some code. So, but the reason I thought I'd present it is because it actually worked. It's the darndest thing. So, what I'm doing is I've got two motors in there, one on each side. I basically fixed the left motor at full speed, and then I'm pitting, if you will, the right motor to keep it going straight. And I'm reading the encoder counts. So, basically, the proportional term is every 100 milliseconds I read the two encoders. The proportional term is what's the difference in the encoders. Every 100 milliseconds, what's the difference between the two encoders. The integral term is the long-term accumulated encoder counts between the two encoders. So that's the integral term. I just keep adding encoder counts over time. So it just keeps integrating the encoder counts. And then the differential term is the difference in encoders on the last reading. So 100 milliseconds ago, what was the difference? And now what's the difference on my current read? And so is that difference getting smaller or larger? That's the ICN minus ICN minus 1 term. So those are the three error terms, if you will, and I just have three coefficients that I multiply them by, and that's my delta throttle, my DT. And I started using the K factors. I started them all out 1, 1, and 1, and I ran it, and it was kind of flailing all over the place. As naturally. And then I said, well, let's just back off on the dynamic term. So I made it 1, 0.1, and 0.1 for the three K factors, and it just was like stable, nice, didn't oscillate. It was just working really great. And so it's kind of cool, and it's easy to implement it on Arduino. There's not a lot of heavy math or anything. It's just trivial. So I thought I'd throw this out there for any of you Arduino guys. But it works, and it's just really handy. Let me see if I can jump to.
Quick question about this.
Yeah.
Do you have a gyro or a 6050 on that?
I don't.
Yeah.
Not so far.
Okay, because you could auto-tune those parameters and not have to guess.
Yeah. That'd be cool. Yeah, I could talk to you about that. Yeah. So this is So there's this nice long straight hallway at work. And I just finally got him before he goes straight. I just tested him on it. The door goes down the hall straight. So I'm really happy with it. It's working out well. Anyway, yeah. So that's fun for that. And then so back to this thing. So remember this? Have you guys seen this? This is the third part of my presentation and it relates to that thing. So this is the Rogue Heat kit from DARPA or somebody like that, right? Yeah, JPL, that's right. And you can order this thing for like $2,500. if you want to make your own like Curiosity style rover, right? But then there's not much in the way of brains. It's got this LCD display or whatever it is on the top, but they don't have like a real computer in there yet or anything like the 2500. You mostly get this Robotics chassis, and it's neat and all, but it's made from this aluminum and it's kind of expensive. So, you know, I don't know, man. I thought I've always kind of wanted to do one of these, and that's kind of where that wheel over there came from. But $2,500 is $2,500, you know. So, anyway, I've kind of poked around with this idea. My girlfriend and I were testing one of my chassis in the backyard the other day.
Is your wife?
Kind of cool. But so I started looking into this a little bit, and you know, that's just an interesting picture because it shows a real good view of the legs and the chassis and stuff and how they built it. So okay, that's neat.
The robot looks cool too.
And yes, the chassis's good. So yeah, so I thought about trying to make something like that, and that's a while ago, like about a year ago. I got started on it, and I wanted to make a wheel. So I have a picture of it in here. I'll get to the wheel in a minute. One of the things I wanted to try was looking at making this chassis for less than $2,500. And I remember these guys at West Virginia Mountaineers did this thing for the NASA thing the last couple of years. And it's sort of kind of like that. It has 6 wheels, you know, and stuff. I think they use skid steering. It doesn't have steering.
Rocker boogie suspension?
Yeah, something like that. They call it something, the rocker boogie or whatever they call it. Yeah, boogie fluid. And it's, you know, it's kind of a similar sort of thing. So I decided to make something like, look into making something kind of like that in less than $2,500. And I did some drawings, crude drawings, my crude drawings. But basically, they made it out of Robotics aluminum, and it's like, I forget how much that is per foot, but it's not, it's expensive. It's like, I don't know, $12 a foot or something like that. PVC is about 80 cents a foot. So I sort of figured out how to make this. It's kind of my crude plan for how to make this out of 3-inch PVC. I can make all the leg sections out of one piece of PVC. It's about $20. And then you can get 6 of those things to make the wheels. That's about another $20, and it's pretty cheap. And that's the line chart. It's the BOM cost. I like the 2-inch, 3-inch, and 4-inch PVC. The most expensive part is the motors. The motors are about $400 if you get 2 drive motors and then 4 steering motors, 6 motors total. It's about $400, $450. So I wanted to make a wheel like this. It's really cool because you don't have a lot of stuff sticking out in between the wheels. If you want a lot of ground clearance, you know, you don't want to have like an axle between two wheels where you don't have much ground clearance. You want something like this where you don't have much in between the wheels. So my idea was to make something like that with this thing, and this was something I was looking at it before. So when you put it all together, it sort of looks something like this. So the motor goes in the hollow side of the wheel, and you fasten it to the center. You have to center the wheel, and you know, there's a mount for it, and mounted the motor in there, and then there's some of the other parts, and then eventually it looks like something like this. And it's pretty darn cheap. You know, it's just this aluminum, a couple of aluminum brackets, and you know, a $5 PVC cap and a motor. And you might wonder, that's going to be really slippery, right? You're not going to have any traction with this shiny, smooth end cap thing, right?
Hot glue.
Huh?
Hot glue.
Yeah, something like that, right? Yeah, so you can get these things from who is it? It's not DF Robotics, it's that other one. Oh shoot, there's a company that makes robots that sells these things. But the other 2 I had was these things. So, you know, you can kind of bust these up or cut them up into pieces, maybe lengthwise, and make some shards that you can then use PVC glue and just glue them around the outside of the wheel. Now you've got something that'll get you some traction. So it's still cheap. You know, it's really cheap. It's the idea. Very low cost. So anyway, that's my idea on that. And then these would be the ones that would mount on the top of that bracket. So you make the wheel and then the bracket that comes out, and then this thing with this servo bracket that'll take the load. So the servo's not taking the load of the robot. This, you know, you can see the larger bearing in the shaft there. That's what mounts on the top, and then that servo can turn the wheel. Because you know, on the Curiosity bot, the corner wheels are steerable, right? That's how you do turns. You turn the 4 corner wheels, and now you can, you know, turn and make turns, spin in place or whatever you need to do. So you can still get that functionality with this approach. Is the idea, and not have to spend $2,500. So anyway, that's kind of my presentation on all those 3 things. And,
You're going to have that ready on the 24th?
it'll be next month. Yeah.
spend a lot of time on your PID function, but there's a wonderful PID function available in the Arduino library.
There is. I looked at that. I was in a hurry and I couldn't figure out how to use it in time.
It's very complete.
Yeah.
I've used it.
When I have more time, I'll look into that.
Very nice.
So I have 2 robots, although I neglected to bring extra batteries for this one, and I left the switch on apparently. But I automated the turning of that. The key to it, and there's a switch in the back, along with a zipper to get into that I added to get into all the internals. And the key to it was a 3D printed pulley that basically was only a part that wasn't off the shelf that I added to this. So.
Is that Tyco? Who makes those?
I don't know. This looks like Spicy Pets, that's all.
Who do they call it?
Feisty Pets.
Spicy Pets.
Feisty.
Feisty. Oh, okay.
Anyway, so yeah, pulley and a string and servo in there, and it will, and a sensor here in the front will, it'll automate it. And so I guess I got it finished pretty quick. And the other one is, I also have one of those LiDAR sensors everyone's been talking about, and and I wanted to play with it and use it, so I actually decided to make my robot do something since this was sitting on my shelf ready to program, and it should not fall off the table, although there is one angle that it will, but you'll be able to see it if it happens. I had to slow it down so that otherwise it'll fall stand with it. So yeah, and actually that's gonna fall. Like I said, there's one angle that it'll fall off.
Let's see if it still runs now.
No batteries.
Well, you gotta put the batteries back.
Of course. No pressure here.
It's a safety feature. The batteries disconnect themselves.
The other thing I did was make sure that it doesn't do anything until you set it down. It seems like I lost some motor. That is one of the bugs that has, it occasionally gets stuck in a reverse position, and I haven't figured out why. And occasionally the LiDAR sensor will, or the rangefinder will give me an error, and then it'll just sit there and not do anything.
That's okay.
It also works on the ground.
All right.
So that's the
best demo of the night.
yeah. Anyway, that's
so this is a mop bot, and I don't know here.
If you reset it, bring it.
okay. Huh.
Reverse.
Something must have come loose.
Is that using that machine learning algorithm?
No, this isn't using the genetic algorithm he had. Although, this is just the default code he has. So we just built, 4 of us built one in about 2 hours, and works surprisingly well, actually.
What are the sensors on front?
So there's there's 2 infrared sensors to detect the edge of the table, and it just backs up and turns when it encounters it. There's a Arduino Nano and a motor driver here, and some AA batteries, which really want to pop out of this holder for some strange reason. And you know, my contribution was, he was using crazy glue, and there's the VHB double stick tape, and I was like, I don't want to use crazy glue, I want to use the double stick.
So I've just been informed by Chris that you get to sign the book. So this robot is a perfect starting point.
Where do I
if you
sign
want.
here? This one?
No, I think I'll go that far. You can do it over here. So a perfect starting point for our TableBot challenge, of which we are running the third phase next month. So if you're more interested in programming instead of the hardware part of the robot building, you can get started with Chris's kit, which he calls the MockBot. And are you having any classes, or how do people build one of these things?
We usually get together about every other Saturday, and it's on the peninsula. It's not down here in the south.
Okay.
Chris
So
tends to announce them on our forum, so.
our Google group?
A lot, yeah.
Okay, so keep an eye on the Google group, and Chris will post there if there's going to be another MockBot building session. All right, I don't think there were any other robots. Are there? Going once, going twice? Okay, so we'll take a 8-minute break. Oh, yes. Oh, so Ralph would like to make an announcement.
So you guys showed up on a very good night tonight. We have 2 very generous donations of giant boxes of parts over there. There's like a whole bunch of metal bits and stuff like those robots are made out of, and boxes of electronics. So they're being given away. Preference if you are a paid up member, and there's a fight, the paid up member automatically wins. They'll be over there. We'll put them out on the table during the break or for afterwards if any good. So it's Logic, Ted from Logic, and Ryan Hickman from TikTok has donated all these parts there.
So please remember, these are for everybody. Don't just take
Bring
them
it back. Bring it back in a robot.
And the requirement is that it must come back in a robot, otherwise it will come to your house and retrieve the item. All right, we'll take a 7-minute break.